I mean, you know, and it's very dated. So in a way, I feel nervous about this. I mean, how can I be teaching seniors and first-year graduates material that'll be obsolete in 5 years? But this is all about how policy is created and when it works and when it doesn't work. And this FERC Order 755 will probably end up being struck down by the Supreme Court as well, but something else will come in its place. And it's an example of something crazy. Well, I'll get to it. All right. So I'm going to go over 45 again, you know, and if there are any questions, please ask me, because it's really hugely different things for almost the same product in a sense. It's really strange. And when you compare these two orders, it blows your mind how sensible one is while the other is so stupid, you know. So remember my ERCOT nirvana. So let's go through this again. Oh, good, just in time. Just in time. So remember the ERCOT nirvana? Or maybe you missed that one. Did you?
Was all blue?
Yeah. This is the nirvana. This would be the economist's dream, that if you have perfect competition, then everything goes down to marginal cost. And that's why I call equilibrium theory the economics of death. There's no more innovation. Every idea has been had, and we're all barely surviving. You know, it's like, it really is. But again, this came from lobbying. Enernoc, this guy, another Justin, is getting a job at Enernoc. They lobbied for. They were saying sort of what I'm saying, without any kind of incentives for demand response, all these wonderful services will never be realized. Without investment, you can't get investment without compensation, and so what Enernoc wanted was to be able to bid in the real-time market. So these 5-minute auctions. So that's this complicated language is to say, please let us bid in the real-time market, and we'll create nirvana for you. Yeah. And so again, FERC decided that they would allow, like Alcoa or aggregators, to bid in the real-time market negawatts. You know, negawatts. Yeah, that's the term. I think that's from Georgia Tech. I think a professor at Georgia Tech coined that phrase. So instead of, I'm going to ramp up my power generation, I'm going to ramp down my power consumption, which is an awesome resource. I mean, I'm all for it. But paying the LMP is what's crazy. So again, that was just a few years ago, March 2011. And immediately the generation companies lobbied and got people like Bill Hogan, hired. Bill Hogan's an economist, no economics training. He's an economics professor at Harvard who is big into consulting and lobbying for energy industry, and does a lot of really good work as well, but some misguided ideas. I suddenly feel nervous being recorded. Anyway, so immediately it died. It had to die is my conjecture, but it had to die because a lot of the industry knew they'd go out of business. I mean, these generation companies that got together and filed a lawsuit, they knew they'd be out of business in a few years with this. And so again, my nirvana, peaks would be shaved, contingency resolved in seconds, because we could do it as engineers. You know, if we were given a motivation, we would just do amazing things with loads, and we would get the ERCOT nirvana, and we'd all be dead. You know, it's really something else. And when I've said this to people in power in economics, they say, "Well, God, yeah, that'll happen." But then people go to business, and then the prices will go up again. I mean, what? So then they'll go up again. Is that a good thing? I mean, And so then people will complain about spikes in prices, and then it'll take 2 or 3 years to get into the game. But the risk will, if everyone knows this is going to happen, once they get back in the game, they're not going to do it. I mean, it's completely absurd to think this is going to work. So again, in this nirvana, there's no business case for demand response. Any idiot can figure out that's going to happen. If you do a good job, you'll put yourself out of business. How can they not understand this? Now, here I'm going to give you guys a reading assignment. I'd meant to do this earlier. So that, again, underline means you can click it and get it. I'll give you details. But Kirby's Kirby has a few survey articles that are like written in baby talk. They are awesome. He's a great writer, and it really is insightful. And he actually has, in this one paper you can click, he talks about the 5-minute market, the hour-ahead market, the day-ahead market, and shows the different prices and actual real-life prices, and actually computes the average price of every case, and they're all the same. So it's just like what we proved, that the average price is like the average, we in a competitive equilibrium would be the average marginal cost. But he's finding the average price for the real-time market is the average price in the day-ahead market. And he says that's a good thing. And holy shit, how can you think that's a good thing, Brendan? You're confusing the ailerons and the jets. You know? I love you, Brendan. You're an awesome writer, but you know, so the thing is, the real-time market, it really is part of regulation. I mentioned about BPA, where they don't have a real-time market. Instead, they have a regulation, this balancing reserves, you know, and those are the flaps and the wings. And to confuse that with an energy market, so the day-ahead market's an energy market. I mean, you're trying to get bulk power, but the real-time market is the error in your forecast. So it goes up, down, up, down, up, down, and so it's crazy. So, So last spring I said, Brandon, you're crazy. We sat down and discussed this, and he said, well, the generators, this does incentivize fast generators, because if I'm a really fast generator, I can hop in when the prices get high and hop out when the prices get low, and I'll make money. And I said, well, Brandon, have you done any economic analysis to see, is that the right payment for that service? You know, is that the right payment? Are you overpaying or underpaying? You know, I mean, is it going to incentivize responsive generators to come in? You know, and there's no, of course not, because, and he's a nice guy, and he said no, it's not. And I said, if people bring in cheaper services, then you'll definitely be underpaying them. You know, so he writes that this is a fantastic thing, that the average prices are all the same. But I say it's the worst thing in the world. You know, and that's sort of a hint that this is true. That, you know, basically that all the prices would even out to this locational marginal price of the lowest generator, and that zero. That means it's so low that nobody would survive. Okay, and again, so in our competitive equilibrium analysis, we know the price would go to marginal value, not marginal cost, very often. And again, that could be infinite. You know, I mean, in Tasmania, it was obviously negative 5,000 at this day, and in Australia, somewhere in Australia, it was $20,000 a megawatt hour during this crisis. So, just saying that again. So the thing is, we need incentives beyond the market. We need incentives beyond the market. There's no question. That's the only point I'm trying to repeat over and over and over again. You know, and locational marginal prices won't do it because they're not incentivizing these responsive ramping services. They're just not doing it. And that's true in the real-time market as much as the automatic generation control we talked about the last weeks. LMPs were a terrible idea for higher frequency you know, power markets. They might be okay for day ahead. I even think they're not for that. I think they're a bad idea for day ahead as well. But I don't know. I mean, I'll stay on the fence on that. But for real-time markets, this is crazy, I think, okay? You know, and it's all right conjecture there. I'm open to debate with anybody, but I can't see any reason for them. So, anyway, it's still gone. You heard that it's in the courts right now, 7:45, and we'll find out in the spring if it survives or not. I hope it dies. I hope it dies.
Yeah. I guess my question is, who would profit or not profit, but who would benefit from 745 passing that?
Well, the ENERNOC, you know, would be selling these products, you know, until they, I mean, the thing is that in the first few years, they make enough money, the CEO can retire. Or get so much good publicity for making all that money, he'll get to be a CEO somewhere else. So in the short term, it's awesome, for companies like Enernoc who can come in and swoop in.
So what is Enernoc specializing again?
So Enernoc does aggregation of things like that I'm interested in, aggregating loads to be able to offer negawatts and bid into the market. They do virtual storage, yeah. And there's not a lot of science yet that I know of. This is all new. And they've only been in the business a few years.
So like,
yeah.
If you were a virtual storage company like Enernoc,
yeah.
you'd be making crazy money.
You make crazy money initially, yeah. And
wherever the location, marginal price is crazy.
Yeah, but the trouble is, but if you're too successful, then you'll put yourself out of business. And that's the thing. You can't be too big.
Right.
Yeah. I mean, if it gets too big, once enough players come in, it's over. Everyone dies. It's
I see.
yeah.
So the theory is not now, but it's like if this is successful.
If it's successful, you'll kill yourself.
That business plan.
Yeah.
And then it'll just overload.
And that's true. I've also been told by economists, well, that's true of every product, But the thing is, with other products, you can have product differentiation. If I'm selling sugar, I'm going to sell some sort of fancy sugar, green sugar that makes people happy. I'll sell paleo sugar. I'll come up with some gimmick. Mac comes up with a stupid cable every year, some wacky thing for disruption.
I feel like also this product is so important.
That's the thing. It's a huge difference.
It's just too.
The fact the entire economy rests on this, and the fact that it's so damn cheap. I mean, the things we're talking about doesn't cost anything. Fuel is cheap considering the value of power, and ancillary services are nothing. They're very, very cheap, and so it's hard to make a lot of money on this anyway. So wasting a bit of money to make sure you have long-term reliable service is worthwhile. But because we want long-term reliability of our power supply. That's the thing. Long-term versus short-term is the biggest issue. For short-term, sure, what the hell? Enernoc will make a lot of money.
So did Enernoc lobby for this order?
Yeah, They were one of the big players getting this in.
So what was FERC's response like?
Yeah, I don't think it took long to get this going. Yeah.
I mean, do you think they were like maybe do this to cheat the system, or?
No. This is because this is the right thing to do. In terms of the social planners problem, damn straight, we want anyone who can help regulate the grid. We want them to be players. And generators are not a great source for all the reasons I mentioned. You pollute more when you're ramping up and down. You're not at your sweet spots. You're not as efficient. Remember heat rates and all that. There's all sorts of social costs. In terms of wasting energy, in terms of pollution, in terms of opportunity costs. I mean, not getting that power from those nice generators. The natural gas generator should be at its perfect operating efficiency, regular power. Be fantastic, and use other resources that are cheaper for the regulation. And so Enernoc rationale that we're wasting all of this potential regulation capacity is dead on right. What's insane is just that. The fact that FERC would say you have to pay the LMP. That's the only thing you're allowed to do. Why not marginal value? Why not? Why do they focus on LMP? Which is the solution to our economic dispatch problem, more or less. If you ignore marginal value, why would they do that? And also, they had all sorts of rules on how big the players can be, and so forth. And they put in all these artificial rules that destroyed everything. Okay.
So you think that this is the right way to go?
Yeah.
Paying location marginal price.
Idiotic. Well, it doesn't fit the problem. I want, remember what I'm trying to get. I'm trying to get that, blah, 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 blah. Those are prices, I know, but it's because I need more power, I need less, I need more, I need less. It's an aileron, I need that, And so the real-time market, it's up 10 minutes or up 20 minutes, down 20 minutes, up 10 minutes, down 20 minutes. That's a service I want, And energy, it's not energy, And so locational marginal prices don't fit the problem. They don't fit the problem for generators, and they don't fit the problem for loads, And especially markets. Another thing.
Like average.
Nah, you'll see what I like. You'll see one completely idiotic idea that works. I want something that works, and I'll explain what I mean by works in a moment. But the other thing is there's a lot of risk to the grid operator because, the economy's good. Suddenly Alcoa says, no, I'm making too much money on cans. I'm out of it. It can just happen overnight, and so so you're basically putting the grid operators at a lot of risk by always having auctions every 5 minutes. And you're increasing the complexity of their auctions as well. And there's so many reasons. I mean, I could go on for hours about why this is nuts. All right, and you don't have to agree with me, okay? I mean, that's why I want to stand by conjecture. But anybody can find a paper that actually has a rational argument for this structure for real-time markets. Let's pass it along. I've never seen one. Now here's...
I feel like for the marginal prices you showed us, like that just wouldn't make sense.
Well, if you look at these examples, this is Illinois in 1998, way before California. I pay these prices. These went to us. That $5,000 a megawatt hour. Did I ever show you this one? This is my favorite. Oh my God, do you mind if a little backstory? So, I was a very underpaid associate professor in Illinois. and they deregulated the power markets in Illinois. And the very first year, that summer, the prices were way too high already. They were $20 a megawatt hour when they used to be 20 or something. And then they shot up because of a hot summer, and they went up to $7,000 a megawatt hour. And the Public Utility Commission said, well, that's too high. Let's put a price cap on. And they put a price cap on of 5,000. And look what happened. The area and the two curves are the same. Did I ever show you this before? No. So I don't know. In 2011, I was at a power workshop in Sweden. And on my flight home, there was an incredible thunderstorm with horizontal lightning, just insane, scary storm. And I got off the plane in Sweden, and I knew there was no way I was getting home. And I walked over to the American Airlines lounge to say, look, I'm not going to even wait. I'm going to get a car and drive home. And in front of me is this angry guy yelling at the woman behind the counter, saying, "Oh, we may get home!" Ah! And I heard him say something about Illinois, and I said, "Hey, I'm going to drive. I'll give you a lift if you want." And so we're walking to the Avis rent-a-car, and we're about to cross the road at O'Hare Airport, and there's a boom crash and horizontal lightning. And I thought, what the hell am I doing? I've got jet lag, no sleep on the plane, and I'm with this crazy guy. And we're getting to the car, and we're driving south, and there's turned over cars. I mean, really, there were several cars that had flipped over. They'd gone off the road because the winds were so high. And we started to talk and did this sort of, when you've got two people who don't know each other well, there's sort of a back and forth, just talk, who are you about? And he said he was an economist from the University of Illinois at Springfield. And I'd just given an angry lecture like this in Sweden. And I said, what area? And he said, oh, in fact, I'm just back from a power workshop. So I said, same here. and it's a 2-hour drive normally. It took us 4 hours. And I started to tell him, well, I just gave a lecture on this, and I mentioned, I looked at these topics, and he said, what did he say again? He made a reference to that professor at Harvard I mentioned, Hogan, and I won't say what he said. But anyway, the reason I'm saying all this, it turns out his name is Carl McDermott. And he was fresh out of graduate school when he was plopped in to be the head of the Illinois Public Utilities. And he was told, deregulate it. Deregulate telecommunications. Deregulate power. He had a few years out of graduate school. And so he did this. So by the time we got to the airport in Illinois, we were both screaming and laughing. We could barely walk. It was just because of the incredible coincidence of us being together. So he's visited here several times. He'll probably be back again next spring. But he did that. He was just told to, without any knowledge of power. He didn't know anything. He had some economics training and knew about supply and demand, and they meet. And so it's amazing. It was Carl McDermott is a great lecturer, and he's on my side. He thinks this is crazy. So I'll explain this crazy figure. some things that look really bad and really good. So the insanity of the slide, which is from Utility Dive, I believe, reflects the insanity of FERC Order 755, but yet I love it, you know? So it's illogical, but it's beautiful, you know, like a flower. All right, so here it is. So again, 2011, new rules for compensating frequency regulation resources. Now, frequency regulation resources, you can see already they're narrowing it down into a very special context, you know. I mean, it could be contingency reserves, a part of contingency reserves or something, but it's okay. But so it requires the ISOs and RTOs to pay regulation resources based on actual amount of regulation service provided, and they say, i.e., speed and accuracy. So that's it. So now they're really mentioning the flaps on the planes. You know, and by the way, there are flaps that are very wide, and they're ailerons. They're different things on a plane, but that's aerospace engineering. Okay, and so again, FERC's motivation, well, again, lobbying like mad. Beacon Energy, who make flywheels, and battery companies, they saw Eninox success, I guess. You know, I mean, they were lobbying as well. And the current compensation for frequency regulation is unjust, unreasonable, and unduly discriminatory. Some people get paid when they're not doing anything, you know. And boy, that's my point about Kirby's slide. I mean, you know, you're paying these guys based on, I mean, that's a real-time market, but I mean, you're paying people arbitrary payments, and it's just not reflecting what's needed at all. And there's going to be a need for frequency regulation services, you know, increasing needs in the future because of renewable energy. Okay, and they hope for an efficient outcome. So according to commentators, allowing the market to establish the compensation for resource performance will allow more economically efficient outcomes. So these are people who have never taken economics course. I mean, you know, I mean they're economists, but they've forgotten what economics is. Can you imagine this? What's the social plan? I'll put this on the next midterm. Define the social planner's problem for flaps in an airplane. You know? Try to do it. What's the consumer's welfare function, and what's the supplier's welfare function, and what's the social planner's solution, and what prices would realize that? You can imagine. Yeah, write it down. You know, it's completely comical. It's completely comical, especially create appropriate incentives for market participants. The only thing I think is nuts is appropriate. What on earth is appropriate? I could never define it. Neither could they. So guess what they came up with? You know? Well, no, they came up with something I love in a way. But so a two-part settlement. It's what I always advocate. Basically, a uniform price for frequency regulation capacity, okay, paid to cleared resources. So there might be some auction once a year. Yes, I love that. So you pay somebody to be around, like a firefighter. You know, they get a salary even when they're not putting out a fire. And a performance payment for the provision of frequency regulation services. And it also reflecting accuracy. I mean, this is revolutionary. Nothing like this has appeared before. You know, I mean, can you imagine not having that? But things like that don't appear elsewhere. When of course you need that. But here's performance. Have I ever showed you this? I mean, I thought I may give you a forward references. There it is.
Mileage.
Okay, so one part is mileage. So it's discrete time, okay? So, but so instead of an integral, it's a sum. And instead of a derivative, it's a difference, but big deal. And we're talking about 4 seconds. So that's, you know, so that's what you get paid. That's part of your payment. So if you know anything, I mean, I can become I can retire in a microsecond. You know, I can just apply a white noise, something that has, you know, some space-filling curve. So it's strange, you know. So what's the motivation? Does it have to do with marginal cost of battery? So something like that. So is it nuts? Let's go through this. And I'm going to tell you it's nuts, and I'm going to tell you it's not nuts. You know, and we'll have to decide. All right. So here's an example. So sort of the midterm had something like this. All right. So So I've got so suppose that the grid operator wanted a sinusoid. Remember I mentioned that arbitrary signals like a Fourier transform can be broken down, approximated by a sum of sinusoids. So, so this is a component. And how many 1 megawatt hour batteries are needed to track this signal? All right? And so that's the power output. So imagine it's fully charged at time 0, and then I guess I need my pointer. So it's ramping up its power output, ramping up, gets to A, and then it ramps down, gets to 0. So it's pushing out power, energy per second, through this period from 0 up to 1/4 omega, because I've got a sine 2 pi omega t. And so the area into that curve is the energy, right? So we have to integrate. Can somebody integrate for me? Is this what I have to do? Well, I do know that it's going to be equal to, a 1/2 pi omega. And there's an A missing, right? That's right, isn't it? Or minus sign, or? The minus sign, thank you.
Didn't B 0 to 2 pi?
All right. What's that? Well, the thing is that...
The upper limit is
You don't need the integrator.
What's that? Oh, no, I mean from. I meant to write from. I'm just thinking ahead. You know how it is. But we don't need to think anymore, right? Because we know that...
No, it's just 2 omega.
2 mega.
Professor?
That's 2 pi omega.
Yeah, that's right. Okay, cool. And so basically, yeah, we know that...
No, it's
I'm sorry, you're right. 4.
0 to 2.
I'm getting myself confused. You're right.
I thought it was from 0 to 2.
Oh, it was 2 all along. Yeah. Sorry. And so I know the cosine of 0 is 1, and that must be 1 as well. So there must be a 2 there. So the 2's must cancel, but there must be a minus sign I'm missing. It must be 1 minus minus 1.
At 2, 1/2.
It's minus 1. Yeah. They have to cancel out. I know the answer, so I'm cheating. But it's minus 1 plus 1. And 1 minus minus 1, or something. Minus 1 minus 1 times minus 1. Okay. So anyway, we can check. Oh wait. There. Yeah. Is that the same? Yeah. All right. So, but what's the mileage?
Mileage?
Yeah. So let's write the mileage. So that's the energy. What's the mileage? Well, let's see. I hope I don't give it away. Okay, good. So the reason I broke this up into these tiny segments is that it's easy to just work on one segment first. So mileage is that's the definition of mileage in continuous time. So they just find discrete time. They have a sum and they have differences, but it's the same thing.
That is the mileage.
No. So the energy. Oh God, that's right. I haven't really finished my. I haven't said this loudly enough. The total amount of energy storage needed to be able to discharge over this period, to be able to supply that curve, okay, is this amount, and that in megawatts. Okay, and so that's why you need more than A over pi omega batteries to supply that service. So that's the trouble. Calculus makes me get confused. But the point there, I should have screamed, is that if the frequency is large, if omega is big, I don't need many batteries. Now, of course, other constraints come in. I mean, the ramp, the fact that velocity, the slope issues can come into play. But the fact that the higher the frequency, the fewer the batteries, roughly speaking, until other constraints come into play. All right. But what about mileage? So mileage is this. It's different. Mileage is the like the length of the curve, essentially, roughly speaking. This integral of the absolute value of the derivative is sort of like the length of the curve. Not exactly, but it's similar to that. The length of the curve has a different formula, but very similar. And so the length of that curve, I mean, that formula we can all work out. I claim here it's just A. I think you can all do that calculus. Is that correct? Yeah. You know why? Because I don't need the absolute values. It's increasing. And so it's just...
It would have been a g of t0 minus g0, which is just a minus 0.
Yeah. See, on this little interval, it's increasing. So the derivative is positive.
The derivation just cancels out.
So everything cancels out. It's just...
g of t0 minus g of 0. And we know that g of t0 is a.
And g of t0 is a. Cool. So that's right. So mileage is really easy to work out over this little interval.
Double it, right?
No, because one of these. So we.
Like we're going. Integration of energy was from 0 to 1 over 2.
No. I'm just looking at a different interval. No. No, this is a different question. So here is to supply that sine wave forever. I would need a collection of batteries with that much energy capacity forever. But mileage depends on the time interval. And so if I've got this little tiny time interval from 0 to t naught, my mileage payment would be A. But remember, omega is the frequency, right? So if the frequency is high, I get all that money in a tiny amount of time. So if I have a big time interval, so the mileage on the next little interval is the same, the mileage on the next interval is the same. They're all the same. So basically, if I have a t over here, I'll just add up all these little a's, and and that's how much I'll get to bring home.
So you're saying that, t is arbitrary.
If t is arbitrary, then I'll look at how many t naughts are in my t. So I'll have to take t and divide it by t naught, And if this was an integer multiple of t naught, it's exact. If it's not, you'll get this. Basically, an approximation here. It would be t divided by t naught. That's why I get a 4 omega t times that payment. Approximation, because I'm not ignoring little partial parts. But isn't that funny? The amount I get paid is proportional to omega. Yeah.
Is T not dependent on what the grid requires?
No, this is just a simple, crazy example. But the thing is that, if you think about reg D, which I'll review, the regulation signal from PGM, which I'm going to really define a bit more carefully in a moment. It goes up a minute, down a minute, up a minute, down a minute. So it's a sine wave of a period of 2 minutes, say. So that's a typical frequency of omega you might see, and there'd be higher frequencies as well. There'd be harmonics of that, but not nearly as much a capacity. If you looked at a spectral decomposition of reg D, it would have a lot of 1 minute, or 2 minute period content. But the main thing is this weird. Look at this. The number of batteries I need gets smaller with frequency. But the amount I get paid is linear with frequency. It's wild. So anyone would say it's completely loony. Crazy. What the hell are you thinking? But what are you going to do? I don't know. Now the thing is that if it wasn't for it would be really loony if there wasn't a performance metric. Because if I could just supply anything I wanted, I'd supply white noise and retire in a millisecond. But there's a performance, you have to follow what they're asking you to follow. And so it's they're not going to ask for some crazy high frequency signal. But still, it's, how did they come up with this? How did they come up with it? I don't know. But you'll see why I love it anyway.
So they introduced the definition of mileage.
Yeah, they came up with this term for some reason, and I'm sure its origin is some battery company who had done this calculus, and they came up with this as one of the specs that and there was a lot of freedom. So the different ISOs were allowed to to formulate their own opinion.
I don't know if you can
Yeah.
exactly explain what mileage is.
There's a definition.
Well, yeah, I mean, numerically, I understand what it is.
Yeah, but what does it mean physically?
Right, like, what is that? Like,
I don't know, you know.
Explain to someone
Yeah,
who knows that.
but the thing is, but you could see here that, you know, that's ramping, you know, so that's the, you know, the derivative is the slope. And that's the thing that has been been a big concern of generation companies. You know, a big slope is a big concern. And so you're looking at the total ramping over a time interval. And ramping's a concern for batteries too. I mean, you know, like the lithium-ion batteries I mentioned, can discharge fairly quickly, but they take a lot longer to ramp up. And so this does, having a mileage payment, incentivize creating technologies that can ramp up and down quickly. You know, so that's
Okay,
yeah,
I understand why.
yeah, yeah.
Substations collect old car batteries.
Uh-huh. Is that right? Very cool. Oh, send me references. Anything like that. The old car batteries. I love it. Yeah. Yeah. I don't know. Yeah. I bet there's a lot of people running around doing that when this started. But now let me explain to you what. So when I first heard about this, like in 2012, I thought, they've completely gone mad. I mean, they've completely lost their mind. And I saw a presentation by an economist at Pacific Northwest National Labs who just, you know, was laughing at this. But now it's my favorite policy I've ever seen. It's the best example of good policy, in a way. I mean, it's not perfect, but it's the kind of thing I think works. So one thing, there was a lot of freedom given to the ISOs. So they were allowed to come up with their own ways of making this work. They could define performance. The mileage thing, I think, was partly gossip among the ISOs. They decided to stick with that. Because they had to convince FERC that they were doing what they asked. But they were given a lot of freedom. So unlike 745, there's a lot of freedom to be given to how to define performance, how to define mileage. I mean, you know, all of this. But look what happened instantly. It's a lot in this slot, but in this page, let's forget the day-ahead market. The real-time market's most important, but they're both there. This is in 2012, before everything really got put in place. The amount of fast responsive services in the real-time market. And you see here, you've got, this is in gigawatts, 2 gigawatts, 2,000 megawatts of capacity of ramping up and down. And it went up by 25% in 1 year. Just people came crashing in to create new services because of these new payments, because of that. You know, SAF batteries in Jacksonville went nuts. I mean, the production line just started pushing out batteries because of this. It just created innovation and also, you know, fantastic business. And the slower stuff went down. Okay, but it's interesting. Even day-ahead markets. Suddenly there were more responsive, faster generators. That might just be. This is also a period when fracking, natural gas was going up as well. So this could just be more natural gas was being installed. But this is batteries and flywheels. This is, you know, so that's one thing. So it did create incentives like that because people saw, my God, I can make a fortune.
So this
Yeah.
makes it like if you're more efficient, you get paid better.
Well, efficient. No, if you can provide that. If you can. Well, there's a performance mandate. If you can pass the rules to be accurate enough to provide the service, then you can get in, and you'll get paid something that, you know, it's something concrete. I know that if I set up my batteries, I'm not going to be in an auction every microsecond, and the price will suddenly fall to zero. I'm going to get paid mileage, and
As long as they supply that for the amount of time that they.
as long as they do, if I'm accurate, you know, and I do what I'm told, I simply, in this case, a sine wave, but whatever, if I follow that regulation signal, I know what I'll get paid. So that you've gotten rid of that risk to the supplier, and we'll see that we've actually gotten rid of risk to the grid operator as well.
Officer,
Yeah.
how do you define the term regulations? I mean, if you want to define the term in terms of two factors, like
Yeah.
X versus Y.
No, regulation is, again, it has a lot of meanings in different contexts, but it's the flaps in an airplane as opposed to the jets in an airplane. So regulation are zero energy, more or less, services to help to to regulate frequency and also voltage, and keep the grid in steady state, just like a plane in steady state. And so this is
It's kind of like reminds me of like how waitresses get paid. They pay like $3 an hour.
Oh, yeah.
To keep all their tips.
Oh yeah, yeah,
So this is kind of like if you can do this ramping,
yeah.
that will give you more tips.
Yeah, but you heard this story recently that the people who get tips are the cute waitresses. Did you hear this? It was in NPR recently. But they're trying to get rid of tipping in a lot of places because it's so unfair. It's just attractive women who make a lot of money, and really great male waiters don't get high tips. It's really bad. There was a survey in New York about this, and yeah, it's too bad. But this is some beautiful thing. So PGA's regulation requirements just went down because the providers of these regulation services, like AGC, an example, this automatic generation control we've been talking about the last weeks, the amount they needed went from, it went down 22% in the first 3 months. It's incredible. And then it went down another 4%. A month later, it just kept going down. Just amazing. So they needed less because it was so accurate. But then here's the joke. They were paying $13.75 a megawatt hour capacity. That's like the A I had before. And they ended up having to pay $38. So it's true that their amount they needed went down by 30%, but the amount they had to pay went up by threefold, right? I think it's roughly almost threefold. It's just really awful, just awful. So,
well, I guess like that like balance each other out, right?
Well, no, it's threefold, and that's just 30%. But but
I'm assuming there's no. I don't think there's a linear relationship between that. I don't think.
Yeah. Well, I don't know. But it was a concern to PJM. And what's ended up happening is they ended up reducing the mileage payment. There's really there's a multiplier here. Times some, I call it beta. So there's some multiplier. I'll call it M. It's not just this. It's this times a constant. And they ended up having to reduce the constant and fool around. But so that was a problem. I mean,
How did they calculate at $13.75?
This is what they were paying for like AGC before the FERC order. And once they had to start paying mileage payments, they had this. But one of the problems is everybody was pretending they could do it. And so the performance specs, there was a lot of fights about what does it mean about performance, and natural gas generators were not allowed in. This was like for flywheels and batteries, which to me is arbitrary as well. If I can supply this perfectly as a generator, why can't I do it? But they excluded generators for some reason.
Because they know they would lose.
Well, I don't know. Yeah, maybe. I don't know. It seems artificial. But they took care. So this is a transient. It's only the first year. And so prices, the amount paid went way too high. But what the beautiful innovation of PJM was, this genius, was to recognize they don't need everything to be that perfect. So it was a way of satisfying FERC and satisfying themselves. So they took the PI signal that we saw before, so that regulation signal that they were always using, the PI, we are doing the homework right now, the output of that PI compensator, and they take a high-pass version of it, and that's what's called Reg D, and that is what they say belongs in FERC 755. And then they have this Reg A, and they said, FERC, no, we're not going to have performance requirements on this, and we're not going to pay the mileage. We're going to use our old-fashioned. And they were able to convince FERC that was okay. All right? And so this is only a few hundred megawatts, which is all they needed, And this is the lower frequency content. So that's how they dealt with it. So they are paying a lot for this, but what the hell? Why not?
I mean,
It's nothing. Well, they're paying more than they did, a lot more, maybe 2 or 3 times more, but they only need 2/3 as much, and it's nothing. And what they get is long-term reliability. They know that forever they'll have people who are going to be, around to take this money. Yeah.
Reg Ds.
Reg D, they've got this high-performance service. They know will always be able to get it. Yeah.
Reg A is.
And Reg A, they
What
don't.
have they been paying before?
Whatever they've been paying before, and here's the difference. So the blue is Reg A, which is a lower frequency than the Reg D. And there's also truncation. And that's part of the contract. I'm willing to provide this service, but please don't kill me. So they have to actually truncate their PI. They have to take their output of their PI compensator and also truncate it to make sure that they can to satisfy a contract. And the other weird thing is Reg D. If you look at its integral over that hour, the next hour, and the next hour, exactly 0. It's reset to exactly 0 every 30 minutes or every hour or something. And again, it's to make it's so they can sign a contract to the batteries and say, we will not, we will give you exactly a 0 energy reg signal. And well, with Reg A, they don't have that requirement. So they have different contracts for different providers. So to me, this is the most amazing success story, even though it's wacky. And this is the thing is that this is basically the rationale for doing this to FERC is that when they get after say 30% of their faster regulation, getting a little bit of high performance regulation, Reg D say, is a great benefit. But once I get to 45%, there's no value at all in having any more service that's high reliable. I don't care about the low reliable stuff. Control is magical. You can get away with errors. It takes care of itself.
So does that mean that Reg D consists of 40%?
Well, no, this was just their lobby. This is part of a document explaining why they had 2 services. So the fact that the people supplying Reg A are not is reliable means PJM is going to be forced to get more of it, but it's cheaper, and there's just some point, ideally they'd like to take, say, 30% to be perfect Reg D and the rest of it to be Reg A, but it's hard to come up with this exact computation. So, but approximately that's what they do. But they do it through filters, and yeah. And this is what they claim. But look at this number here. This is what they claim from in their document, which is not exactly what they saw. But the first megawatt of fast regulation offsets 3 megawatts of slow. So that would support your statement. The 3-fold pricing increase is worth it. So anyway, again, underlines. You can read all this if you want. If it's 2 in the morning, you can't sleep. Especially read that if you can't sleep. Just any of these FERC reports. So it's cool. So last year, they called this a point of diminishing returns in the document. And Kelly, who was a great student last semester, said, they're wrong, it's there. So that was fun. So Kelly was a student sitting right there last year. That's the point of diminishing returns, when it's 1. Really it's there. All right. So here's the thing is that PJM found that even poor performing services were trying to get into this program, and they had a lot of trouble discouraging them. It's not there's a lot of rules put on these ISOs, and they just can't say no, you're out, you're in, and so they have an incentive to try to follow these Reg D signals, even if they're only capable of following 50%. It's confusing because that's already in FERC ruling that you have to be high performance. But PJM had to go and lobby to FERC to say, hey, we're in a bind because people are demanding to get into this market, and they're not good enough. And so there are more FERC orders. And that's the other one you should know. So I'm not going to go into this, but FERC Order 784 makes more precise what we mean by high performance. And again, it says it has to be new storage, electric storage technologies. So it sounds like it's excluding the kind of things I'd like to do with alternatives to storage. But the main thing here is that they'll take into account, just saying again it was already in 755, but it's more clear, that you have to take in speed and accuracy of regulation services. It's very hard to distinguish this from 755, but it's just underlining it. And OATT is well, TT is transmission tariffs. So every balancing authority has to have a tariff explaining all their products. Operation area, I guess, transmission tariff. But again, let's stop. What time is it? 2:48. Yeah, I need a break. Let's take a break. But any questions on this? I mean, it's sort of I don't know. And tell me later, like when you do the evaluation of the course, you know, it's weird. I've never taught a course where I talk about these sort of policy issues and these very descriptive things. It's new to me. You know, I'd like to get feedback. It's hard. Probably more reading assignments might be a good idea. But yeah. But I want to talk about the bind we're in with all of this alternatives. Yeah. All right. So let's just break for 5 minutes and. So this is the sort of thing they're starting to do, and they're way ahead of us in a way, but we're ahead of them. So back when we heard about this, so I was at Illinois at the time when all this was going on, and actually I was consulting for United Technologies on building efficiency, and it was the most boring topic in the world. I think I mentioned this at that power meeting, that efficiency in buildings, besides hardware, there's not much you can do, really. I mean, there's my co-author, Prabir Barua, there would disagree, Probir Barua, that you know there is a lot of control systems that are quite important in buildings, but mainly it's a matter of recommissioning. You know, it's an adaptive control thing. You have to, the buildings change every year, and you have to retune the PID controllers, and if you do that, you could save a lot of money. But but anyway, but back in actually 2010 or 2009, we had a big NSF grant on energy efficiency in buildings, and and when this FERC order business came out, I did my own lobbying to move it completely to get into virtual storage. And I was at Illinois, and Prabir was here at Florida, and we started to work at getting this building to be a virtual battery. And the idea is that we just right away, just think of a building has thermal inertia. And just like a spinning machine has mechanical inertia, this thermal inertia in a building, and it's storage in exactly the same way. There's no difference. So we're sitting in a gigantic battery, and its value is huge. And so we thought this will be trivial. Let's go in and hook up some equipment to this building and show that we can track a regulation signal. And Reg D, we didn't know about Reg D as we were doing this. I mean, everything was happening at the same time. It was really, really wild. And it's really useful to go through this because things were not as easy as you'd think. I mean, you'd think, what the hell? These buildings have continuously variable equipment, you know, like fans that could be ramped up and down continuously. They have computers in the building automation systems that are connected to the internet. So I can sit at home and turn things on and off. You'd think that what's there to do? There's no science here. But it turns out there was, and we learned a lot. And the main thing is you know, we'd like spinning reserve. This is outdated. Oh my God. So a lot of these slides are from a talk I gave when we first did this in 2012. And Jesus, I wish I had done a little more time proofreading. Because spinning reserves, yes. That's one thing that was missing, like in those FERC orders. We don't just want frequency reserves. Spinning reserves, remember, are generators that are, that's a typo really, but forget it, it's still true. Spinning reserves are generators that are not hooked up, but they're sitting around in case of a contingency. If something goes wrong, you can slap them on to replace power that was lost. Well, definitely it's true, even though that's a typo, I'd say. Virtual storage and real storage are very valuable in a contingency to smooth out the shock to the grid. But there's a question that always comes up. How do you compute baselines if you use a load as a virtual battery? All right? So you know, P is used for too many things. So this is megawatts, say, or kilowatts. It's the load. You know, this is the over say 24 hours. This is the load, and then I decide to get into this game, and I say, well, I'm going to provide this. You know, and am I going to be paid the difference on what I would have consumed and what I did consume? How on earth would they know what I would have consumed? Now guess what? At PG&E in California, Pacific Gas and Electric, they pretend they know. So if you get involved and supply virtual storage, basically, like mainly like, you know, for peaks and power, they say, I know you would have consumed 12.2 kilowatts, so I'm going to pay you the difference between what you would have and what. And you know, it's crazy. I mean, and I have mentioned this before. Of course, I'm going to game the system. I'm going to try to fool PG&E to think I was going to consume less power or more power and fool around. So this is always asked, and it's an absurd question if you do things right. You know. I mean, this only comes up with people thinking about real-time auctions and things like that. In negawatts, that's another problem with negawatts, is what would you have consumed? You have to have a baseline. You know, when you say I'm going to reduce my consumption, you know, suppose I'm going to do that, that's the negawatts. How do you compute that in the FERC 745 business? So that's something that people actually have papers on. Here's a formula for the baseline. And I mean, Jesus Christ, any formula you come up with, I'll go with some scheme to fool the software to make you think I was going to consume more or less. I mean, it's a game. But so basically you don't do that with batteries. Batteries charge, discharge, charge, discharge. And if we just ignore this nonsense, this is a thing of obsession in the industry, just ignore it, we'll do a beautiful job and provide the service that these grid operators want. So just this is noise. When people talk about baselines, it's a fashion that's been around for the last decade. It will die. You'll see, mark my words. Okay, so there would be scribbles in the blackboard, but I don't have any. Does it say a bit more about this? I guess those are the scribbles. So why buildings? They're awesome. I mean, so think about Florida, how much energy we waste in Florida. All, you know, yeah, I'm freezing, but I mean, I mean, so much electricity in Florida in particular is just burnt up in air conditioning. Yeah, we spend it, okay. And HVAC is 40% of the 70% of electricity. It's amazing. So of course we could be more efficient with this, but the fact that we're so wasteful here means we're much more flexible. So we have much more much more capabilities here. Again, I haven't done my homework. I slapped this in without enough preparation. I forgot what R8 stands for. It doesn't matter. But they have, like I just said, they have large thermal capacities, that thermal inertia. So like if you change the mass flow error rate in these fans, unfortunately, again, I'm scared of noise pollution. But in terms of indoor air quality, that includes carbon dioxide and how much CO2 is in the building, and temperature. Nobody's going to feel a thing. That's something special about the U.S. compared to Europe. Here, there's standards that you have to have so much fresh air brought into the building per hour. to make sure you have enough oxygen and get rid of the carbon dioxide. In Europe, they just open the windows. Yeah, which is pretty miserable. It can be miserable. Yeah, but that's one of the reasons it's so cold and humid places in the U.S. is that to bring in all that fresh air from the outside, they have to get the moisture out, which means cooling it. And it would take a lot more energy to heat it up again. So they dump that cold, dry air into the buildings, and we all freeze. So in southern places, it's cold. There is a justification. It doesn't explain why in California you're just as cold. In a dry climate in LA, you're freezing in the summer. It's funny. So one thing that's exciting in a way is that these variable frequency drives in commercial buildings that can be continuously ramped up and down the speed. It sounds really good. And you'd think big deal, ramping up and down speeds in motors. This is a high-tech thing. It involves power electronics, a topic I know nothing about, but it requires some high-power power electronics to make it happen. And that's why it's quite expensive. Okay, so we thought that was a fantastic thing, and now I have my doubts. I'll explain that at the end. All right? That's such a big deal. So I'm not going to go through this, but this is Pugh Hall, like just one floor of Pugh Hall. And there's a gigantic tank of chilled water somewhere, which is for a neighborhood. And then there's valves here for the cooled water. And there's a variable frequency drive fan that blasts air through ducts that go through these different ducts and into the different zones, and to regulate the temperature and the carbon dioxide, and bring in fresh air. And then return air comes like that, and some of it goes out because they need to bring in fresh air. It's a standard. You have to bring in so much fresh air per hour or something like that. And then you can go through all these details, and don't worry, I won't bore you to death. But people spend spent decades trying to model buildings, and the kind of things you look at are the inside temperature, the thermal capacitance of the building, which is, like inertia. There's a wall thermal resistance comes up, how much insulation there is, outside air temperature, inside, and forget the rest of this. There's issues, and for us, there's going to be this fan speed that's going to be important, and the fan power, which will be this deviation. It will be the negawatts, which could be negative or positive, because remember this. We're talking about a zero energy service. Remember, we're trying to, I'll show you an example in a minute. Now, here's where things get kind of tricky. Is that we've got we've got the supply airflow rate, which is something that building operators want to control, and that's roughly proportional to the fan speed. And of course, there's dynamics there, and then the speed of the fan is proportional. It follows dynamics according to our set point. So there's a knob on this variable speed drive. If we turn it instantly, the fan doesn't instantly change. It's a low-pass filter, okay? And we can get this model, all right? And so this is the control input we have here is a deviation in fan speed, and it's because it's a variable speed drive we can do this continuously. One problem is that the power consumption from the fan is like the speed cubed, and that's a problem, but you linearize. We do that in control all the time. And so you'll get an RLC, a resistor, inductor, capacitor circuit model for control. Yeah. It'll just be it'll be a simple linear system. It'll be a simple. It won't be a band. It'll be like a low-pass filter. Yeah. But so we thought, Jesus, this is so simple. We'll identify a model, and we'll be done. We'll walk away. The signal will come in from PJM or whatever, and we'll move you up and down, and it'll work. And it didn't work. It was complete failure. It did not work. And that's because our models were crappy, and they depended on everything. Any model we came up with would depend on all these parameters that would be changing every hour. And so it was complete failure. And we need more control, that's all. So we can get away with a crappy model if you can close the loop. And if you do things open loop, if you pretend your model works, if you just deviate this up and down, pretending you know how deviations in fan set point map to deviations in power, then modeling error is going to kill you. But if you have feedback to take into account what the actual power deviations are, you can make it work. And that's what we did. So we were able. So we had a particular architecture for this. And I'll explain this slide. So the very first time I presented this was in 2012 in Illinois, right after I'd moved here. So I moved to Florida, and I flew back to give a lecture at Illinois. And this was a mentor of mine when I first moved to Illinois, a professor in control. And I had 2 slides. And the first slide had Milton Friedman, the economist, in dollar signs, and had prices to devices. Yeah.
What is pi stand for?
Where is that?
Proportional integration.
Where?
PI building.
Oh, PI, just like in the last lecture, it's proportional integral. Yeah, PI control. So this is just really the reg signal. This is actually PJM's reg D signal. And I'm not giving you details, but all I'm going to say is this. Is that we needed a local controller. Okay? And then we have a big black box here. Now we came up with some hokey model based on linearization and so forth to delta P of t. And that would be like delta PL of t, like our notation before. Okay? But let's not do that, that's confusing. So this is a fan. All right? And then we went through and we did our own compensation. Another G sub c. There you have it. So we were able to measure the power deviation from the fan, right? And we were able to then measure the PJM reg D signal appropriately scaled and take the difference, which is what we called E before, but this is local, just in one building, and pass it to our compensator, and guess what? PI, just some simple control. I'm sure proportional probably would work as well. And until we could close this loop, it didn't work. If we identified this model and just tried to pretend we knew this model, it failed completely. So you needed local control. And that's something we learned from this experiment, that the only time this is going to work is when you have local control. That's a mantra. If you're going to create virtual storage, that's one lesson from this. Okay, so I'm not going to have a tombstone, I'm going to be burnt, but if I was going to have something on my tombstone, that would be it. Because now to me it's obvious, because one thing is that performance metric. We did it because we wanted to make sure that we track PJM signal better than any battery. We wanted to kick their asses. Just absolutely, just do it. Just make sure it was perfect. But and we knew what the building. See, we knew the baseline because we knew what the building compensator, the building automation system was asking for, and we were just perturbing what it was asking for. So we secretly knew the baseline, and we were perturbing it. But so first of all, you need it to make sure we really are making that error go to zero. We're giving the PJM what they want. And number 2 is to make sure that the building doesn't suffer. So the building monitors its own quality of service. Air quality in terms of fresh air, temperature, all of that. The building itself needs to monitor that. So intelligence means designing this compensator and for both objectives, the local objectives and the global, the grid objectives. That sounds trivial, but it's only us that have done this. There's no other work who did that, believe it or not. I mean, it's really strange. A trivial observation, it seems, but it was, yeah, isn't that funny? There was a thing that worried us a lot. So Prabir, who was an expert, much more than myself in buildings, said that this won't work because the building system already has a PI compensator. So if you mess around and there's a building, in this building, when the temperature goes down, the power ramps up. The building automation system itself will fight back and end up consuming more power because it's going to be fighting us. It's going to see us as a disturbance, right there. So how do you avoid that?
Put another controller there.
Well, yeah, you could, but the thing is you could redesign the whole thing. So you could just basically take out the building automation system and start from scratch. You go back to the Bode plots for the grid itself. And here's one change I'm going to make in the course the next time I teach it. I'm going to change every one of my omegas to an F, because omega should be the grid frequency. I realized that like last week. So F was what I called omega before. We should do that. It looks like this, because this is PI control. So I'm talking about its current design. So every building, commercial building in the country, you'll have a PI, and that'll go up, I guess. But it's trying to eject disturbances here. So it's okay, so if you had a low frequency disturbance, so basically you had somebody open the window for an hour and let a lot of hot air in, then the temperature would increase, and then the PI compensator would see that disturbance, and it would crank up the cooling so that you would end up reducing that low frequency disturbance. It's all designed for low frequency disturbances, And so it's high gain in a certain region, but there's a sweet spot here where the gain is low. It's not worried about fluctuate disturbances in the order of timescales of 5 or 10 minutes. So you just take advantage. We know that the building automation system, the PI controller for the building, doesn't give a damn about frequencies of order 5 minutes. So you just do that. So you restrict the bandwidth of your deviations outside of the bandwidth of the compensator for the building. And that's how we got things to work.
Oh, so you design.
We make sure we only allow deviations in this frequency band.
So you couldn't perform
No way. We couldn't do anything out here without completely changing the control system for the building. And so this is our bandwidth.
But that's all you care about, right?
Well, that's all we cared about at the time, because we saw the FERC order 755, and we thought, and we saw the Googlebot Nest around the same time. We were screaming, about the potential. Because we really felt like we're at the head of the curve, And the thing is, you really need to be, if I wanted to retire, then I could have gone and tried to find a company to go with. I just like academics too much. It's a shame in a way. But so this was FERC order 755 was our motivation, and that frequency band is way out here. So it just was a perfect match. Now, in Berkeley, at Lawrence Berkeley National Labs, they've been working on using buildings as batteries for 20 years. But they've always been here. And they've always had this problem. So there'd be, like a peak. They would put in a control system to reduce the power consumption, and they get massive blowbacks because of the building control system. And they never solved it, if you ask me. They never resolved it. Yeah.
That's like an oversight. Why did they try?
Well, it was because of the needs. Two things. I mean, there was it was a case in California that the biggest concern was a peak. So this was their initial motivation was before way before FERC Order 755, before all the more renewable energies. The world has changed quite a bit. But also, I'd say LB&L didn't bring in control people. They had building experts, but they didn't have any experts in control. And so, if they did, I think they would have gotten a lot further. Because I think you could do it. I think you could actually get buildings to provide regulation in lower frequency ranges on the order of an hour. But you'd have to completely redesign the control system.
Or you have to account for that when you design the building.
Yeah, that's true. But you'd pre-cool people. First of all, you'd have to tell people, hey, it's going to be a little colder than you like at 10 a.m. and a little warmer at noon. You'd have to have a contract. Will you accept a 3-degree temperature deviation? Yeah.
That's a big deviation.
Well,
it's like from 81 degrees to 78. That's a hot.
No, but how about 69 to 72?
That's super cold.
Oh, how about 70 to 73?
That's also super.
Well, I'm going to show you something that'll blow your mind, though. Watch this. So here's an example. So anyway, so there's a fight. There could be a fight between our control system and theirs. That's theirs, and so this deviation we're inserting could be seen as a disturbance, like I mentioned. And so again, this is just showing what I said before, is that this dashed line here is the closed loop. So this is the open loop. Okay, so if you have this PI compensator that's infinite gain at low frequencies, the closed loop transfer function is g of 1 plus g, and that's why it's flat at low frequencies but crashes down. And so anyway, so we end up fixing a frequency band where there's a bandwidth that's unseen by the PI compensator. That's all. I don't really need all that. So the HVAC system doesn't attempt to reject the disturbances. And again, if you change the fan up 5 minutes, down 5 minutes, nobody will feel a thing. It's only noise. We didn't hear it in the experiments. We didn't notice it. I mean, because it wasn't that. This is there are all sorts of other fans. Okay. And so we did simulations, and this is why we thought we could do it open loop at first, because when we did simulations, our predictions and the measurements seemed perfect. But that was a model under one set of operating conditions, and then it just didn't work in practice. So when we closed the loop like I described, we could track a reg D signal perfectly. That high frequency stuff is measurement noise, because we can't get perfect.
Well, there are some places where the noise is just maybe a little too much. How would you get right there?
What's hard to measure, we need better equipment for measuring power.
Oh.
Yeah, we really do. This is in minutes here.
Do you think it's just the quality of your equipment, or?
Oh no. When we take power, it's quality of equipment. I mean, what we're using to measure power, which is part of the building automation system, we need something better.
Still has to.
Oh no, we could get better technology. We should do it.
Okay.
We should do it. It's just that we didn't.
So you like some cheapo stuff.
We haven't. We've had no incentive to go back. We just said, hey, look, it works perfectly, and now we need. We don't have any reason to. It would be nicer for presentations for sure. I'd like to just for presentations. I'd like to buy some better equipment for measuring this. And if we get this big DOE contract this month, I'll find out. It's like a $5 million, which we'll have a microgrid on campus if it comes through. Then we'll do it. We'll pitch money for this. And so in terms of how much you can get, these air handling units have a 25 kilowatt motor, and we're only going up and down 10%. So we get 3 kilowatts of regulation reserves, that's the language they use, from this. All of Pugh Hall has 3 of these, so it's 10 kilowatts. And but that's, we're being really conservative. And so for 100 buildings, it's a megawatt. So the University of Florida can supply a megawatt of these services. Florida could basically regulate PJM. All of Reg D could just be gotten from buildings in Florida, commercial buildings in Florida. And that's just fans, which are ridiculous. I mean, these are tiny loads compared to the amount of energy that's involved in the chillers. And talk about thermal inertia. I mean, chillers are beautiful, toys for storing energy. And that's that Ice Energy article I sent to all of you is a version of that. I feel like I'm missing something. God. It's not here. Well, I was going to show you. Well, anyway, go to Pugh Hall sometime soon. If you look at temperature, it goes up and down. There's a hysteresis control. So Justin, you know what this is? This is Pugh Hall today.
Temperature?
Yeah, guess what that is?
No idea.
It's more than 3 degrees. It's around 3 degrees.
Well, like, what's the bottom, what's the top?
So it's something, I think it's like 71 to 74.
Okay, so that's you can do that.
No, but all I'm saying is 3 degrees. I don't care where it is.
Okay.
Yeah. Yeah, and so that's I see a vision for the future, is that you're allowed to set basically if you widen your hysteresis band, you'll get a bigger payment per month for services to the grid, because the wider this band, the more capacity of ancillary service you can provide. So that's the thing, is that I don't think there's an open question anymore. Obviously, besides these sort of reserves, the Reg D, balancing reserves at Bonneville Power Administration, by the way, BPA, they're awesome, of course, for contingencies as well, because you need, the governors come into play, and that's the highest frequency, but you need all sorts of, we have a contingency, you lose 100 megawatts, you need all sorts of resources at every time scale for dealing with that. So of course, buildings are useful for that. It's not an open question, it's just such a small thing compared to what we're talking about. The baselines is a joke. I mean, this ridiculous thing about somebody telling me what I would have consumed, forget it. It's right there. The idea is this, is that an aggregator or a utility company will install the equipment, and they will take all control out of your hands. The consumer is not allowed to do anything besides accept that equipment installed in their building. And there's a contract for, if I allow this equipment to be installed, then I'll get a capacity payment and a payment for services rendered each year, or each month. And just like FERC Order 755. But so that way, all the responsibility is to whoever installed the equipment, an aggregator or a utility, and they designed it to work, And so you've taken the consumer out of the picture. The consumer just says, I want these constraints on temperature. I don't want to have to pay more for energy, or if I do, I want compensation, and I want some really predictable compensation back. All right? And if the grid operator or an aggregator installed that equipment, they know what they installed, and it's designed to track this damn signal. So all those issues go out the window, and I don't know why. I mean, this is controversial. It makes me want to scream. This is controversial. This common sense approach to this, even though it's done in a lot of places. I mean, again, the example of Florida Power and Light having contracts with consumers to shut off pools or water heaters in terms of when there's a crisis. That's done today. So why not do it at this larger scale? FERC Order 755 allows that for the first time, and Internuc's aware of that. and most sensible companies are picking up this model. It's the academic community that's hard to talk to. I mean, they don't accept this model at all. Most academics, I don't know why. But one picture, I don't know why it's not here, is that it's a picture that shows that this is the nominal behavior of the building, and with our control in place, you can't see any difference. So we had no control in place, and just during one of these cycles, we stuck in our controller, and it just looked like a triangle wave still. There's no change at all. Which means we're being too conservative. I mean, 10% is too small. We should be doing 20 or more, So that's it. So this is a real question to you. I mean, I think, tell me, or think about it. Is there anything off the top that we've missed? I can think about, it's one thing that I haven't told you, but maybe you'll think of it. What's missing from, why isn't this the perfect virtual battery solution?
The weather outside is so nice you don't need.
Yeah, there it is. So there's two problems that concern me with this particular example. One is noise pollution, that people will hear, in some buildings, people hear deviations in fan speed, say, and that'll cause problems. Although the fans do deviate already quite a bit. And the second is capacity changes with time, and maybe not in a completely predictable way. So that's why I don't think you would just use commercial buildings alone for Reg D. They'd be augmented with other resources. And whether that time-varying capacity is an issue or not, I don't really know. I mean, I doubt it, but it's an open, that's an open question. Anything else? Any other? I don't know. I mean, I guess I want to mention one other. So I told you I know nothing about power electronics. And when I mentioned all this to Shuo Wang, who is a new professor in the power group here in EC, he said, well, these variable speed drives, they're not so great. I mean, it might be cheaper to have these as on-off devices. So, we're thinking, wow, we're so lucky to have modern buildings with these devices. But he said that you actually might be cheaper to turn them on and off. And so that's a question we'll talk about. So what if we didn't have a modern building? Or what if Shuo Wang is right and we should just turn these things on and off? So already, I mean, examples like refrigerators whose power consumption is on-off. But according to Shuo Wang, maybe even if it isn't on-off, it'd be cheaper to make it on-off. I don't know. But also there's lithium-ion batteries. How do I draw this? So a lithium-ion battery, remember, it could discharge quickly, but then it took a long time to charge. So that was like 5 minutes, and that was like 30 minutes. And maybe it has an ideal charge and discharge rate, which would make it last the longest. So we'd like to preserve that. Just like a fridge has an ideal cycling, which makes sure the fish are fresh, but also minimizes the energy consumption. Given these sort of constraints on loads, can any of you imagine tracking, some of you can because you know my research, tracking that? So how would you get a load that wants to do that, or a battery that wants to do that, to do that? you know. And I have mixed feelings about getting into details on this. It's my own current research. It has to do with the lecture I gave at the Power Club last week, or Monday, and it's that Google Research Award. I don't know. So I'm still sort of pondering the next lectures. I think I'll give a short lecture about how you can do it, about how you can take on-off loads and get them to track a reg signal like this. And things like fridges are fantastic, because talk about predictable. I mean, you know, we know how many are there. We know how much they consume. If we could make these do that, you know, how cool is that? You know, and so you don't have the problem of time varying capacity like you do with a building. You know, and lithium-ion batteries as well are awesome for that purpose. But again, that cost issue here. Fridges are free. Everyone has a fridge. Yeah. So, all right. So so the next parts of the course are still. I'm adapting. I'm trying to think of what's best for you all. But I think it's worthwhile. I think I'll talk a bit about how to deal with on-off loads and at least ways to think about it. But that's enough for today. Until next time. Oh, but any questions about the homework?